All right, hello everybody. Make sure you have turned in your vocabulary worksheet to the sub, and let's get started into our next unit, which is chapter 10 and 11. Chapter 10 is over gas laws, and chapter 11 is over states of matter. So today we're going to do an intro into the kinetic theory, and we're also going to start talking a little bit about gases and how they work and different properties that they have. All right, so the first thing is talking about the kinetic theory. So the word kinetic means motion. So anytime you are moving or dealing with some sort of motion, you are showing kinetic energy. So the kinetic theory of matter says all particles of matter are in constant motion, even in solids, but is so slight that it is hard for us to see. So everything we deal with on a daily is moving in some way, shape, or form. Even though we view it as a stationary object, it is, in the molecular level, moving. So how I think of it is things like your iPad and your table and your chair that you are sitting on, they are vibrating ever so slightly. That's because the molecules themselves are so squished together that they don't have any room to move. Now, compared that to a gas, where a gas has a ton of space to move around, they can move at a quick speed and pace, and they are constantly in motion. Same thing with liquids. Liquids can easily move and flow and slide past each other. We'll talk more about that when we get into liquid states. But those molecules are also ever moving. So that is what we're talking about when we're talking about the kinetic theory of matter. So the word gas comes from the Greek word meaning chaos. So numerous experiments have led to the evidence that suggested the following behavior of gas particles at the atomic level. So as you can see in the little graphic here, those gas molecules are constantly moving, and it is chaotically. It is moving off things, they ricochet off each other, they ricochet off other objects, and they bounce and collide and move in all sorts of different directions. There's no rhyme or reason to how they move. They just hit to the next area they go until they hit something else, and they keep going into a different direction and keep moving. Okay, so these properties they have at the subatomic particle level. So gases are made up of tiny particles of a negligible volume, so meaning that it is very insignificant. They're so small that we don't really notice the mass of them. So gas particles are far apart, and they do not attract or repel each other. However, there is an attractive force between the particles of a solid and a liquid. So gas particles do not repel each other, they do not attract each other, they just are moving so fast and their mass is so small that they can't stick to each other. Unlike solids and liquids, for example, like liquid water, loves to stick to itself. Those attract to each other. Solids, the molecules stick together. The only way to break them is if you break them apart physically. And so those particles like to stick together. Gas doesn't have that. It likes to do its own thing because of the super small volume it takes up. And so it can just kind of stay together. Particles move independently of each other. And this is why gas expands when it fills in a container. So the word diffuse means it likes to move outwards. So that's why this first part here is gas can expand to fill a container. It can fill whatever shape you want it to be. If you want a star balloon, if you want a circle or a triangle, you can have any weird shaped balloon you want, is because gas fills up whatever container it's in. The shape of a room can be whatever shape you want it to be because the gas in the room is going to fill up that space. It does not care. The word diffuse, all that means is it's going to spread out. Gas does not just contain to one single area, it's going to move. So one way I have taught students in the past to think of diffuse is like a diffuser. If you have a scent diffuser at home, the scent is the strongest right where the diffuser is, but it's then going to move the scent throughout the rest of your home and spread it out. The same thing, if we use the example of a fart. Farts diffuse throughout the room. My dogs are prime examples. They will fart on one side of the room, and one person will cover their nose, and then it'll move to the rest of the room to then take out the rest of the people. Because gas particles diffuse, or move throughout a space. They don't like to stay in one single spot. Gas also has no definite volume, and what that means is there is no certain volume that is its limit. It can fill whatever space it needs to, nothing really stops it, and so whatever volume you have, that's what you have. There's no definite volume that it can take up, unlike a solid object is whatever the solid object is. It can only take up that much space. Volume, or for gas, it takes up as much space as it wants. 2, gas particles move very fast. Very, very fast, like thousands of kilometers an hour. So an example, when a bottle of ammonia is opened, doesn't the entire room eventually smell it? Or, for example, things like bleach. Yes, you're gonna smell when you open a container of bleach and you leave it open, the whole room's gonna smell like bleach. That's because those particles move so quickly and spread out and diffuse throughout the entire room. Because they move randomly in straight lines until they collide with something or each other, and then it'll then move in a different direction. So those particles just continue moving until they hit something, and then continue in a different direction until it hits something else, and then continues in a different direction. So when you open a container that has a very strong smell, it's then going to spread out throughout the rest of the room. And it won't stop until it's fully diffused. Okay, so we call this a random walk. So gas particles will move in a straight line until they collide with another particle and then change directions and then repeat. So it's this never-ending cycle of continuing a straight line, hit something, ricochet in a different direction, continue on that path until it hits something else, ricochet moves in a different direction, and just continues that way for all of time, constantly moving. Again, they have a ton of energy behind them. They move very, very quickly, so they can just collect, move on. So it's just why we call it the random walk. There's no rhyme or reason to it. It just move in a straight line until you hit something, ricochet, move in that line until you hit something, ricochet into a different direction. Third one, all collisions between gas particles are elastic, meaning they do not stick together. So when these gas particles hit each other, unlike water's going to stick to itself. Solid, those molecules stick to each other. Gases, they just bounce. They just hit each other, bounce off. I use the example of, you've probably seen the videos of people running with exercise balls at each other, and they hit each other and they bounce off in the opposite direction. That's the same thing. That's an elastic collision. They don't stick. They just hit, repel, and go into a totally different direction. Kinetic energy, represented by Ke, can be transferred from one particle to another, but kinetic energy is never lost. So that energy is continuously moved throughout the system. That energy is never lost throughout it. So kinetic energy, so for example, if you're on a roller coaster, when you're going down a hill of a roller coaster, that's a ton of kinetic energy you're building. So it's going to take that kinetic energy and it's going to just transfer it so that the car then moves down the track to the top. Okay, so kinetic molecular theory. It has 3 major assumptions with gas particles. The first one, their particles can move in a straight line until they collide with each other and particles or the walls of the container. So they're constantly moving in a straight line until they collide and move into a different direction. The motion of the particles is constant and random, so it's constantly moving in whatever direction it decides to move in, and there is no attractive or repulsive forces among these particles. So they do not stick to each other, they do not repel each other, they just hit, ricochet into whatever random direction they decide to go in. 4 variables that are generally used to describe gas. We're going to use each of these. We use pressure. That can be in kPa, so that's kilopascals. We have mmHg, which is millimeters of mercury, and atm, which is atmospheres. We also are going to talk a lot about volume. So this is hopefully a reminder from chapter 9, we used volume. So volume is either in liters or milliliters. We talk about temperature, which is always going to be in Kelvin. So we do not use Celsius or Fahrenheit. We stick to Kelvin. And then we talk about the amount, which is always going to be in moles. Most of these we've already talked about, except for that pressure is the only one we really haven't talked about, or temperature, at least when we get into Kelvin. Okay, so here's our different variables. When it comes to pressure, We have kPa, which is kilopascals. It's another way of measuring. We have millimeters of mercury. So that's just the amount of mercury that can move throughout a system. And then atmospheres. 1 atmosphere equals 760 millimeters of mercury, and 1 ATM equals 1.01.325 kilopascals. A lot of times we're just going to use that 101.3 when we're doing kilopascals conversions. For temperature, it's always going to be in Kelvin. So Kelvin, so 0 degrees Kelvin, is 273.15 plus whatever degrees Celsius. So you will have to convert. Generally, we just stick to 273. So if you need to convert from Celsius to Kelvin, you just add 273 to whatever your Celsius is, and that will get you to whatever many Kelvin there is. Okay, factors that affect gas pressure, because this whole chapter is really about gases and how they move and how they affect each other. How does temperature affect it, and pressure and volume? Okay, so the effect of adding or removing a gas. So the amount of gas in a given volume increases, the pressure is going to increase. So think of filling up a balloon. The more volume there is, so the more gas particles there are in there, the stiffer the balloon's going to be, the firmer it's going to feel. That's because you're increasing the pressure within it. So if we double the amount of gas, so if the one on the left has only 5 molecules of gas, while the one on the right has 10. So we're going to double it. So the reason there is more pressure is because there's more molecules inside. Makes sense. The more molecules inside, the more collisions that are occurring, the higher that pressure is going to be, compared to the one on the left where they have more space and they're going to run into each other a little less. So it's going to create less space or less pressure. So 2 times the amount of gas is 2 times the pressure. When particles mean more collision, which means more pressure. This is called a direct relationship. So if the number of particles doubles, the pressure will double. If we triple the number of particles inside of a container, it's going to triple the pressure. So direct means they're going to move in the same direction. So if one goes up, they both go up. So here is a real world application. So whitewater rafting. I've never been whitewater rafting. Maybe you have before, but we've all dealt with inflatables of some kind. So the strength and flexibility of the raft are important when you go whitewater rafting. So think about it. The raft must be able to withstand the pressure of the air inside of the raft and the force of the rapids below. If the raft is too inflated, so too much gas is inside, the raft will easily burst. So you could bust a seam and then you're not able to hold air anymore, and then your raft deflates. If there's not enough gas is added, the raft is not going to be able to float. So we've probably all been there where you have your floaties in the summer. If there's not enough air, it's not going to float. It's just going to sit there and it's going to sink. But if it's too inflated and someone, let's say, jumps on top of it, you can easily burst and break your floaty or raft in this situation. And so you have to find the right balance between enough air molecules to allow it to float, but not so much pressure that it's going to then burst because of the rapids underneath or the pressure the people are adding on top. Okay, our next one is the volume of the container. So when the volume of gas decreases for a given amount of gas, the pressure increases. So for example, the one on the left is a pretty decent sized container, which has the same amount of molecules in both. So we have 5 molecules here in a bigger container. Then we shrink that container in half on the right, but have the same amount of gas, same number of particles. The pressure is going to increase in the smaller container compared to the bigger container. The reason for that is because the volume, the amount there, the size, is shrunk by half. There's more collision can happen, so that means more pressure. While the one on the left, our normal size container, it has plenty of space for them to move and continue its normal pressure as before. So we know this as a indirect relationship. So particles are closer together in a container, which means more collision, which really means more pressure. So it's indirect. So that means if the volume is halved, the pressure will double. So that means if we double the volume, the pressure will be halved. So that means if one goes up, the other one must come down. So if the volume goes up, the pressure is down. If the volume goes down, the pressure goes up. So that would be an indirect relationship. So here's an example. We've all done this. Open soda cans and bottles. Soda can and bottles are usually opened slowly because we have learned that popping them open too fast can cause it to fizz up and spill all over the place. When you open the can or open the cap, the gas is suddenly able to increase its volume in order to decrease the pressure inside the can. If you shake a carbonated beverage, causes the gas bubbles to mix with the soda before some of the gas can settle out, and you've got quite a mess on your hands. So we've all done it before. I'm guilty of it too. I have little siblings. You go pick up, especially bottles, work the best. You take a bottle, maybe take a drink out of it, you close it up, and you shake it. And you hand it to somebody that doesn't know that you've already shaken it. When they open it, the pop flies everywhere, all over them. They get mad, you get a good laugh, so on and so forth. So what's happening in there is that when you are shaking it, the gas it's no longer able just to settle out. You're now mixing it back in with the soda, and that's what's giving the soda enough bubbles to allow it to spill out. You're also going to increase the pressure because it's not able to let go. But the minute you open that bottle or the can, you're then able to let the pressure out, and then it's going to spill outwards because it's trying to relieve that pressure all at once instead of then being stuck. Because we are now increasing the volume, it'll then decrease the pressure, but it happens at such a rate that it's not able to decrease fast enough to not spill everywhere. So now you know there is a science behind why shaking bottles of pop will explode all over somebody. So if you increase the volume, you will decrease the pressure. If you decrease the volume, you will increase the pressure. Our next one is temperature. So when the temperature of a gas increases, the particles move fast. So they have more kinetic energy, and so they're going to move faster. That also means the pressure is going to increase. So if we have our same containers, and we have the same number of gas particles, but we're going to double the temperature. So the one on the left has 298 Kelvin. The one on the right has 596 Kelvin. It'll be 2 times the temperature will mean 2 times the pressure. So the more temperature something has, or those gas molecules have, it's going to increase the pressure. And so that would make something easier to explode when it's warmer, because it can move a lot faster. So think of when we have to go outside, especially if you're a spring athlete. The beginning of season, it's really hard to get going and trying to get into running outside or just being outside because you're so cold. You just want to sit there and huddle in your sweatshirt and not move. But when it's getting warmer out, it's a lot easier to get yourself to be outside and move around a lot faster because you have more energy and it's warmer. And so when you have a higher temperature, it's easier to move around, and so those molecules start bumping into each other more often, and so it's going to increase the pressure of those containers. So the particles move faster when heated, and they strike the walls of the container with more force, which means pressure will build. So this is a direct relationship. So if the temperature is doubled, pressure is going to double, and vice versa. So if you drop the temperature by half, the pressure will drop by half. So we have to be careful when we're watching things that are pressurized, because if they get hot, you're going to increase the pressure, which means things could explode a lot easily. So an example would be aerosol cans. So gas in a sealed container can generate an enormous amount of pressure when heated. So when you have something that is completely sealed with gas inside of it, there is a ton of pressure within it. So there are labels on all of your aerosol cans. So whether that is hairspray or sunscreen, spray paint, anything that's a sort of an aerosol spray, it'll say do not store above 120 degrees Fahrenheit. The reason for that is because with that, when it's heated, it's going to create so much pressure, it could just explode. And then you have whatever substance all over whatever building that's in or container it's in. So even empty aerosol cans can have some gas in them. So they will explode if you throw them into a fire. If they get super hot, they're still going to explode because you're never going to get it empty all the way. So it is wise to not store cans at a temperature that will freeze the substance in them. So freezing cans causes the substance to expand and then will puncture the can. So that's why you have to be really careful, especially in the wintertime and summertime. So if you have sunscreen, let's say, and you're going somewhere that's really hot. And again, your car is always going to be hotter than the actual temperature outside by several degrees. And so you have to be careful with your aerosol sunscreens, because if it gets too hot, so especially on our nice hot Nebraska days when we start hitting the hundreds and your cars are getting to 110, 115, 120, the aerosol inside of that is creating so much pressure inside the can, it could explode. Now, is the probability of that happening high? Not really. We don't get too hot here, but there's other areas like in Arizona, they actually have to be really careful about that, of not leaving them in their cars. Same thing if they freeze. A lot of times they'll say do not store below this amount of temperature, because when you do, the substances inside are going to freeze together, because a lot of times it's a liquid that is then pressurized with some sort of gas, and then when it's stuck together they're going to freeze, and then that will still cause the can to then expand, or the product inside to expand, and then that will then puncture the can, and then you cannot use that product anymore. And so it could burst a can open. So you have to be really, really careful when you're dealing with any sort of aerosol product, and making sure it's not being stored at too hot a temperature, but also not too cold of temperature as well. Okay, so that's all I got for you today. So your homework tonight is for the Intro to Gas Law worksheet. The sub will have it, so make sure you get that completed. A lot of it is talking about what type of relationship. So you can go back through here and go back through your notes to figure out what type of relationship would be within each one. Tomorrow, make sure you bring your calculators. We are going to get into Boyle and Charles law. So if you have any questions, let me know. You can also start working on some late work as well, because that'll be due on Monday. If you have any questions, let me know. Have a great rest of your day, and I will see you tomorrow.